In the fall, we studied variable forces. So, for example, one of the first ones we studied was the spring force. And the spring force was for an ideal spring, Kx, where the K is the spring constant and X is the position. Now, you may notice that on the AP exam equation sheet, you will see a negative sign inserted there. That's to correct for the displacement. So when the displacement is positive, the force needs to be negative, pulling or pushing it back to the equilibrium. If the displacement is negative, then the force would need to be positive, pointing it back towards the equilibrium. So that's why you see the negative sign in the equation sheet. What we did is studied the magnitude of the spring force, and then we put the direction in our problems as we were drawing our free body diagrams. So don't think that the AP exam equation sheet is smarter than you are, because this is just to correct for the direction of the force when we're really just focused here on the magnitude of the spring force. And then we draw our free body diagrams to indicate the direction. So another force that we studied a little bit was the drag force. So we set up a experiment with coffee filters, right? And we released our coffee filter. So initially the velocity was 0, and the force acting on our coffee filter was the weight, and that means that the net force on our coffee filter was just Fg, which would be equal to ma. So the initial acceleration was the acceleration due to gravity, the gravitational field. Now, as the coffee filter fell, it reached a terminal velocity where, it stopped speeding up, just was floating downwards. And so in that case, we had the same gravitational force acting on it here. And if it has reached a constant velocity, if v is constant or terminal, then the acceleration must be 0. And if the acceleration is 0, that means that the tension force must be equal to the weight force, or the drag force must be equal to the weight force. So then with that, we knew that the drag force was equal to the weight. Now, we then studied what this meant and collected data. So the data we collected was so we could manipulate the drag force indirectly by manipulating the weight. So we put the weight on this horizontal axis, which was the drag force, okay? And then we graphed the terminal velocity, v sub t, on the horizontal axis. And we saw a trend that as the weight increased, thus the drag force increased, the terminal velocity approached like an asymptote. And that looked a lot like a square root function. So we came up with this idea that the terminal velocity is proportional to the square root of F drag. Or that force drag is proportional to V terminal squared. Okay, so in this case, this force that's acting on our coffee filter between the moment we drop it and the moment it reaches terminal velocity is changing depending on the velocity. So that means that somewhere in the middle, when we have our coffee filter and the weight force is constant, the drag force acting on it at that point in time is less than the weight because it hasn't reached terminal velocity. It hasn't reached a point where the acceleration is 0, okay? So, it is common to have forces that depend on another variable, or like I said, variable forces. The spring force depends on position. The drag force will depend on the velocity, as we saw in our lab. Let's look at a case where an object is falling, and it is falling through the air, and it has a mass m. The resistive force acting on it is equal to c, which is a constant, times v, velocity, and the unit for the constant is kilograms per second, and the unit for velocity is meters per second. So let's do this first. Determine the terminal velocity of the object. Now, just from our recent discussion, force of gravity acting on our object and the drag force. And in the case of terminal velocity, the drag force is equal to the weight. So that means that my C times V is equal to M times G, which means that V would be equal to mg divided by c, and that's my terminal velocity. It's a special velocity for this problem, or for this case. So now, what if we want to determine the velocity as a function of time as it falls? What we first want to do is write the differential equation for the motion from the time it's dropped until it reaches terminal velocity. So from t equals, or from 0 to t terminal. So this is the time in which the net force is not equal to 0 but equal to ma. Now this word differential may make you queasy, okay? It's not intended to. A differential equation is just an equation that has a dx dt or dv dt or some sort of derivative function embedded in the equation. So for our question, our net force would be now, because it's falling down, I'm going to let the down direction be the positive direction, just like we've done so many times. So I'm going to have F sub g minus F drag is equal to ma. So remember, this is the case where the gravitational force is down, but our drag force is up, and it is not equal to the weight yet. And because it's moving down, I'm going to let the positive direction be down. So now to make it a differential equation, we just substitute what we know here, and F sub g is mass times the gravitational force minus our CV is equal to ma. Now, mass is a constant, the gravitational field is a constant, C is a constant, V is a variable, mass is constant, and A is a variable. And A and V have a relationship, and that is that our acceleration is dv dt. So if I substitute, so mg minus cv is equal to m dv dt, then I have a differential equation. This is my differential equation. Now let's determine the velocity function with respect to time for this object from or between 0 and t terminal. Okay, so we have the differential equation above. So what I see is I have a dv dt and a v, and they are separated right now. And so what I need to do is get my velocity v on the same side as dv so that I can evaluate it. So I'm going to write this as, let's see, mg minus cv is equal to m dv dt. So I'm going to multiply by dt on both sides, and then I'm going to have m dv over mg minus cv. Now I could rewrite the right side just a little bit and have it as dv over g minus cv over m dt. So if I integrate this, the left side, integrate the right side, and I'm going to integrate this from 0 to t, so some time, and I'm going to integrate this from 0 to v, some velocity, and I'm looking at it, between 0 and t terminal. So some time interval that's going to be less than t terminal and some velocity less than v terminal. Now, I don't know offhand how to integrate this. So I'm going to use the u du substitution. And so if u is equal to g minus cv over m, then du would be equal to negative c over m dv. The g is a constant, so the derivative of g with respect to v is 0. Okay, so that means that if I do a substitution, dv will be equal to negative m over c du, which if I substitute back into my derivative, I'll have negative m over c du. I'm going to integrate that du over u. Sorry, because the u is the g minus cv over m, which is in the denominator. So m over c is just a constant. So that'll pull out, and then the integral of du over u with respect to u is just the natural log of u. So then this would be equal to negative m over c ln of u. So let's go back and put this up here. So now we can substitute, and the integral of dt from 0 to t would just be t evaluated from 0 to t. And then the integral of dv over g minus cv over m evaluated from 0 to v will be negative m over c, the natural log of g minus cv over m evaluated from 0 to v. Okay, so then we've got t is equal to You know what, let's go ahead and multiply both sides by negative c over m, because then that way we don't have to deal with that being on the right side of our equation there. So then we can evaluate then ln of g minus cv over m minus the ln of g minus 0. Using your natural log rule, so that would be the ln of g minus cv over m over g, and that's equal to the negative ct over m on the left side, okay, which would make this the ln of, let's see, 1 minus cv over mg. That would be equal to negative ct over m. Oh my gosh, we're looking for the velocity, and it's still buried over there on the right side. So we've got to get it out of that function there. So let's see, if I raise both sides to the natural log e, so e to the negative ct over m would be equal to 1 minus cv over mg, then let's see, I would have that cv over mg is equal to 1 minus e to the negative ct over m so then the velocity would be mg divided by c times 1 minus e to the negative ct over m. And this equation is an exponential equation because t is in the exponent. So what does that look like if we think about a velocity versus time here? And if you graph 1 minus e to the negative x, you would get something that looks like our velocity and time. And again, it is actually an exponential function. And so this tells me that my velocity is proportional to the negative e to the negative t. So that is an actual time where it is appropriate for you to use exponential. So what can I determine from this graph? I can determine the terminal velocity. The terminal velocity will be that asymptotic velocity there. The time that it reaches will be my t terminal. So that's my t terminal, and this is my v terminal there.